A hexagon, a perfect hexagon, each side longer than the diameter of Earth, sitting at Saturn's north pole, made entirely of wind, rotating once every 10 hours and 39 minutes. It was first seen by Voyager in 1980. It was still there when Cassini arrived in 2004. It was still there when Cassini died in Saturn's atmosphere in 2017. It is, as far as anyone can determine, still there now. No other planet has one. Saturn's south pole has a vortex too, but it's circular. The question is not just how the hexagon formed. The question is why it's a hexagon, why only at the North Pole, and why it has persisted without distortion for at least 4 decades in an atmosphere where every other feature changes constantly. This is the last video of the first month of this channel, and the register is different. The previous 11 videos were about systems, contracts, budgets, institutions, technologies, detection networks. This one is about something simpler and harder. A planet that does things our models describe but don't fully explain. 3 things, specifically. The hexagon is the first. What we know. The hexagonal shape is a jet stream at roughly 78 degrees north latitude, with wind speeds approaching 320 kilometers per hour. Inside it, a polar vortex spins, a hurricane-like storm with a clearly defined eye, 50 times larger than a typical Earth hurricane. The hexagon itself extends roughly 100 kilometers deep into Saturn's atmosphere, based on thermal imaging from Cassini. In 2010, Oxford researchers reproduced polygonal shapes in a laboratory by rotating a tank of water at different speeds at its center and periphery. The differential rotation created stable vortices along the boundary between the 2 flow regimes, and those vortices shaped the boundary into polygons. By varying the speed differential, they could produce triangles, squares, pentagons, hexagons, octagons. 6 sides emerged when the parameters matched Saturn's observed wind profile. A 2020 Harvard model went further. A 3-dimensional simulation showed that smaller cyclones surrounding the polar jet stream compress and pinch the larger flow into a polygonal shape, like smaller rubber bands squeezing a larger one into a shape with edges. These models are credible. They reproduce the hexagon. But they also raise the next question. Why do Saturn's conditions produce exactly 6 sides and not 5 or 7? The lab experiment showed that the number of sides depends on the speed differential between the jet stream and the surrounding atmosphere. The models match the observed hexagon by tuning their parameters to Saturn's measured wind profile. But they don't predict the hexagon from first principles. They explain it after the fact. There's a difference between reproducing a result and understanding why nature chose that result. Saturn chose 6. The models say 6 is consistent. They don't say 6 is inevitable. And there's the stability question. Earth's hurricanes last days or weeks. Saturn's hexagon has lasted at least 44 years, from Voyager 1's flyby in 1980 to the present. The atmosphere around it changes. Cloud colors shift from blue to gold across Saturn's seasons, which each last roughly 7 Earth years. The hexagon persists through all of it. When Cassini first imaged the North Pole in 2006, the hexagon was emerging from 15 years of polar winter darkness. It was still there, unchanged, rotating at the planet's internal rotation rate as if it were bolted to Saturn's core. No atmospheric model fully explains that kind of stability in a turbulent fluid environment. The hexagon behaves less like weather and more like geology, except it's made of gas. The second mystery is the wind. Saturn's equatorial winds reach approximately 1,800 kilometers per hour. That's roughly 1.5 times the speed of sound on Earth. Jupiter has fast winds too, but Saturn's are faster, the fastest sustained winds measured on any planet in the solar system. The source of energy driving those winds has been debated for decades. On Earth, wind is ultimately driven by solar heating. Differential warming between the equator and the poles creates pressure gradients that drive atmospheric circulation. Saturn receives about 1% of the solar energy that Earth does, and yet its winds are an order of magnitude faster. The leading hypothesis is that Saturn's winds are driven from below, by internal heat leaking out from the planet's core, left over from its formation and from slow gravitational contraction. Saturn radiates roughly 2.5 times more energy than it receives from the Sun. That internal heat differential could drive deep atmospheric convection, powering the jet streams from the bottom up rather than from the top down. Cassini's final orbits provided a crucial data point. By measuring tiny variations in Saturn's gravitational field as the spacecraft skimmed through the gap between the planet and its rings, scientists determined that Saturn's high-altitude winds extend at least 8,000 kilometers deep, roughly 15% of the planet's radius. This was deeper than most models predicted. The winds are not a surface phenomenon. They are a deep structural feature of the planet, rooted in processes that operate thousands of kilometers below the cloud tops. Try explaining to someone that a gas giant's weather extends deeper than the diameter of Earth. The numbers make sense. The intuition struggles to follow. The third mystery is the rings. Saturn's rings are iconic, the most visually striking feature of any planet. They're also surprisingly young and surprisingly temporary. Data from Cassini suggests the rings are between 100 million and 400 million years old. Dinosaurs walked the Earth before Saturn had its current rings. The solar system is 4.6 billion years old. The rings have existed for less than 10% of that time, and possibly less than 3%. What formed them? A destroyed moon, a captured comet, a collision? Remains uncertain, and they're disappearing. Ring material is constantly raining onto Saturn, pulled inward by gravity and dragged by the planet's magnetic field. Cassini measured this quote, 0, and found it was occurring faster than earlier models predicted. At current rates, the rings may be substantially diminished within 100 million years, a blink in planetary terms. The ring system we see today is not permanent, it's a snapshot. Galileo first observed Saturn's rings in 1610. Though he didn't understand what he was seeing, he called them ears. In 1612, the rings disappeared from his view entirely as Saturn's tilt brought them edge-on to Earth. Every 15 years, the same vanishing act repeats. In early 2025, Saturn's rings were again nearly invisible from Earth's perspective, appearing as a thin, bright line through telescopes. The rings are thin, extraordinarily thin. They span roughly 280,000 kilometers in diameter, but are only about 10 meters thick in most places. The ratio of width to thickness is comparable to a sheet of paper the size of a football field. That such a vast, thin, dynamic structure has persisted for even 100 million years, while simultaneously losing material to ring rain, suggests there are replenishment mechanisms or stabilizing forces that current models haven't fully characterized. There's something worth sitting with about Saturn. It's one of the most studied objects in the solar system. Cassini spent 13 years orbiting it, collecting terabytes of data. We have detailed maps of its atmosphere, its magnetic field, its gravitational structure, its ring composition. And yet, the hexagon's exact origin is still debated. The wind depth was a surprise. The ring age was a surprise. The ring rain rate was a surprise. Each new measurement from Cassini revised, rather than confirmed, what models predicted. This is what makes Saturn interesting beyond its beauty. It's a test case for the limits of planetary science. We can describe what Saturn does. We can build models that reproduce some of what we see. But the planet keeps producing data that the models didn't anticipate, which means the models are incomplete, not wrong. There's a difference. Wrong models contradict the data. Incomplete models match the data they were built to match, and then fail on data they weren't built for. Saturn keeps providing the second kind of surprise. And there's no follow-up mission planned. Cassini was the last dedicated Saturn orbiter. No space agency currently has a funded mission to return. Everything we learn about Saturn's atmosphere, its rings, its hexagon from this point forward, will come from telescopes, ground-based and orbital, looking from hundreds of millions of kilometers away. The most detailed data we'll have for decades is what Cassini collected before it burned up in 2017. Scientists are still publishing papers from that data set. They will be for years. But the questions those papers raise, questions about wind depth, ring origin, hexagonal stability, may not be answerable without going back. And going back isn't on anyone's schedule. Try explaining that to someone who assumes we've figured out the nearby planets. Hale has found that the assumption runs deep. Saturn has rings. Jupiter has a red spot. Mars is red. Known, cataloged, understood. The reality is that Saturn is a planet where a geometric storm the size of 2 Earths has been spinning for longer than anyone has been watching. And the best explanation we have is underscore, underscore, quote, underscore, 2, underscore, underscore. That's not an explanation. It's a demonstration that the shape is physically possible. The cause, the deep mechanism that selects 6 sides, maintains them for decades, and produces nothing similar at the South Pole, is still open. That's a good note to end a month on. 12 videos. Contracts, budgets, rockets, psychology, interstellar visitors, and a planet made of gas that does things physics can describe, but not yet predict. The common thread, the thing that connects a $4 billion rocket to a $75 million lander to a hexagonal storm, is the gap between what we know and what we assume. Systems that look functional until you read the audit. Timelines that sound plausible until you check the pattern. Models that reproduce the hexagon, but can't explain why 6. The next month goes further. Different scales, different problems, same approach. Find the gap between the official version and the data, and see what lives inside it.